All right. Good afternoon, everyone. I'm Jamieson. I'm a product manager on our Chrome media team at Google. And one of the things that we look at is how to get media faster and better over the web. So I thought it would be interesting just to take a look back at a very boring slide from how technology's progressed from the 80s to now. And a few things have changed. Kind of the first one that's the most obvious is the form factors have gotten quite a bit better, and things just look cooler these days. But the more interesting bit is just the change in how we consume media and how it's changed from having cassettes and CDs and that sort to more streaming and getting everything just on your personal device. But the other thing that's really interesting that's changed is just the models on how we consume the data. And there's kind of really two big models today on how we do it. One's through apps, which we're kind of all familiar with on our phones or our television sets and all this different stuff. But the other way that we consume a lot of content, think YouTube, Netflix, Facebook media, is all through the browser. So there's really these two kind of competing sets of ways to access data that really gets you to the same point. And today, if you look at what types of content we're consuming, it's a ton of video, it's a ton of audio. Now, once we move to AR, and this slide is just showing how we're going to progress, in the near term towards mobile phone-based VR headsets, or maybe Vive-based headsets, Oculus, those sort of devices, and then AR type of either phone-based AR or headset-based AR. The biggest change I see coming is this move to the content becoming three-dimensional. And that's interesting in itself, but I think there's going to be a constant in how we consume media. It's going to be either through apps, just as we have on our mobile phones or on Netflix, but in kind of a 3D interface. And you're already seeing this sort of stuff in the Vive, in Daydream, and those sort of applications. But there's another thing that way to consume that is through the browser and what we can do with presenting AR and VR through a browser. And the biggest change is that this content is all now in three dimensions, whether that's video, that's audio, or it's even the geometry content that we're sending. And this is becoming a ton of data that we need to get down. Now, I think if you are at the show and you're at the expo, you'll see a lot of great content and a lot of great examples of stuff being built as apps. But what you don't see a lot of is what's going on in the web VR front. And I think this is particularly interesting. It's a big opportunity because there's a lot of unique things about the web that we can take advantage of as developers. And it's really about what it means to the consumer. It's just these lower barriers of entry to download an app. You don't have to get the entire package right away. You can just get the parts that you want. As a developer, you can constantly update the content and make sure that the end user has the latest and greatest version of your application. And also just the inherent discoverability and linkability that you have with the web in order for users to find your content. They don't have to dig around through app stores and that sort of thing. Now, these are all great. There's some disadvantages, and I think the elephant in the room is the amount of data that needs to be streamed and the amount of content that's necessary for web-based VR. Now, the analog that I can go back to is we've already kind of solved some of these problems for two-dimensional and traditional media on the web. And if you look at what goes on when you make a Chrome request or an Edge request to YouTube to get content, it's really trying to get this massive stream of data now it's 4K content down from where we serve it through the app to your browser, and how we can do that as efficiently as possible. And at Google and other companies, we've done a lot of great work around video compression. And at Google, we've kind of moved a lot of our content to using VP9 as a compression technology. And what this graph or this world chart is showing you is just when we rolled this out, what it means to the end user in terms of their load time. And if you see the load time, it's gotten a lot quicker when we've moved to VP9 when compared to H.264 and other video codecs. And what that really means to the end user is that they end up, whenever they have faster content, it means that they're watching more videos. And why that's so, and it's really about the user experience. They're getting content faster, they're experiencing less buffers, and in a lot of parts of this globe, especially where you see it's darker, data is not free. It's actually quite expensive. So having efficient transmission of that data becomes just quintessential to users using the content and also just their enjoyment of it. So I want to just kind of look at what the landscape looks like of what media is today versus where it's going to be going. Right now you see a lot of just 2D content, mono, stereo, maybe multi-channel audio. But as we start moving towards VR and AR content, this content, like I said, is going to become three-dimensional. You're going to have 360 video and stereoscopic. You're going to have fully immersive spatial audio, and then a whole host of new geometry options that are going to have AR and VR implications. Now, I think there's already been a lot of great talks, and there's going to be a few more talks throughout the week about 360 video content. What I want to talk about now is just what we're doing around audio and geometry specifically. So just so we're clear on kind of the types of content you're going to see in 3D audio and 3D geometry, if you look at this as being like traditional audio where you have, say, 5.1, 7.1, 2 speakers, it's really, the speakers are in fixed positions around the user, and the user just kind of exists in that space. As we start moving to more AR and VR content, users kind of have an expectation of having a headset where content's rendered binaurally. And in that environment, the entire sphere of sound around them needs to translate when they move their head, because it doesn't make sense if you have, say, a car in front of you and you turn to the left and the car is still in front of you from an audio perspective. It should totally shift around you as a sound sphere around the user. How we capture that content today is through a series of different microphones. So there's these ambisonic microphones, and I'm going to get a bit more detail about what ambisonic means in a few minutes. But they're really these capsules that can capture in multi-directional, and it can go anything from like four individual microphones as an array all the way up to 28 with varying degrees of expense. I think on the far left it's about $300, and on the far right it's about $40,000. So there's quite a bit of range in terms of capturing this content. The other way you might want to do this is through synthetic content, which you could create through a digital audio workstation, where you can place these sources in space, project them on the sphere, and then be able to transmit them. Now, for 3D assets for geometry, I think we're pretty much familiar with this sort of thing. A mesh, which is a whole bunch of triangles. It's been around in gaming for just about ever. What is less prevalent but becoming more interesting are point clouds. And point clouds have been around in scientific use cases for a long time, using LiDAR data to be able to map this entire room as a series of points in space. It's a tremendous amount of data, and it doesn't have a ton of consumer impact just yet, mostly because the LiDAR data or the LiDAR sensors themselves are so expensive. But as we see that these things becoming more and more readily available, being able to transmit this amount of data and have this perfect representation of 3D worlds becomes much more interesting, especially for AR. Because then you can do sort of things like this, where you see this 3D mesh that's been projected into an environment, where this environment could be then mapped using point clouds or meshes. And if you saw the HoloLens presentation today, they had a great example of kind of cursory meshing of the world. So if you could take that another step forward with point clouds, you could get a really, really detailed representation of, say, this room, and then have objects in there like in really good space. So the challenge then becomes, how do you get this data from, say, your production environment, whether you're doing that in Maya, you're collecting that data from an ambisonic microphone, LiDAR, whatever, and get that over the web to a browser. And what we've worked on is a number of compression technologies. All this stuff is open source, and I have some links at the end, which would be great for everyone to check out. But one of the technologies we work on is Opus. And Opus is an audio codec that's been around for a number of years now. It was started by some Ziff folks who are Mozilla engineers, and we've had some contributions from Google over the years. And what we've recently added is the idea of spatial audio to Opus, and how you can transmit a whole bunch of audio content over the web pretty efficiently. And the way we do this is through a technique called ambisonics. Ambisonics have been around since the 1970s, but really never found a home until recently with the advent of VR and AR technologies. And what this allows you to do is using those microphones and using your digital audio workstation is be able to project sound on a 360 sphere around the user and then ultimately render that content down binaurally to the ears. So then when the user moves around in this 3D space, they're getting the exact same sound field that they would in reality. And how we do this is through spherical harmonics. And what this really is a really complicated math diagram that really just says, hey, the more of these spheres that you add, the better precision that you're going to get in representing the full sphere around you as an individual. But the challenge is as you start getting more and more of this precision, it takes more and more bits. So what we typically do is say for okay content, you can get around with first order ambisonics, which gives you some pretty good spatial recognition around, say, your head, but not much elevation. As we start moving down to like third order and fourth order and et cetera, you start getting more spatialization in the up and down direction and behind you. So what we've seen in the past is, I wanted to do a comparison of where we are with this technology. So when we transmit stereo today, it's typically 128 kilobits will get you decent quality audio using Opus. So for ambisonic capture or for ambisonic transmission, for first order, you need a minimum 4 channels. So if we do 4-channel audio at the same bit rate that we were going to do stereo, it would effectively double, so 256. With the new compression that we've had or we've added, we're able to save about 25% of the bits and get a reasonable sound down at 192. When we move to more realization of the entire sound field, it gets really, really complicated because you start talking about 16 channels of audio. If you look at 16 channels of audio at 128 kilobits for 2, you start looking at a meg per second of audio, which is crazy. That's just a ton of data going through the pipe. What we've been able to do is get that down to about 384 kilobits, which is 70% off of what the total bandwidth could be, and get that sounding very reasonable. The other thing that I'm really excited to talk about is Draco. This is an open source compression library that we've introduced in January for compressing 3D meshes and point clouds. I have a couple of examples. So this is kind of a boring model of a bunny. It's a pretty standard computer graphics model, but it's a ton of triangles. It's about 64,000 triangles, and it equals about 1.2 megs. What we've been able to do with Draco is get that down to 73 kilobytes, which is something like 25x compression on geometry, which is huge. And probably the most important thing for this is the decode speed. We have it at 35 milliseconds right now, which is practically real time enough for a lot of transmission over the web. Anything around there is good. We've actually made significant improvements on that in the last couple months. This is another 3D scene. It's hard to tell from this picture that it is 3D, but you can kind of see that it's been captured and there's some tears in the thing. But it's a pretty large geometric piece of data, and it has a lot more interesting stuff. It has colors, connectivity, positions of all this stuff in space. So the original was 40 megs, and with Draco we were able to take it down to 2.6 megs. So if you can think of like transmitting an entire VR scene over the web, this is going to be kind of essential to kind of getting that down and getting it a realistic performance for users. I have a video actually just to prove that this is real. So this is an example comparing it to zip. And as you see, this is like 2.4 million triangles. And without Draco, it takes kind of a long time to load. I think that was like a 7x compression or 7x difference in terms of rendering speed. Actually, that video is old. It's from January. We're about 35 to 40% faster today with the most recent pushes to our GitHub. Kind of wrapping up, so I think the main takeaways from this session is that the web is a viable VR platform, and then I think there's going to be a number of improvements in the upcoming years that are going to make that even more true. We're going to need a lot of data, and to make that possible, these compression technologies are going to become vital to make that happen. What I'd like you to take a look at is kind of where we have this code. You can download all this stuff open source. The Opus Codec's been around for a long time. You can get that now. And the Draco GitHub is available. Please check that out. It's a new project, which is exciting because we're getting a lot of super useful feedback from people that are using it and been able to respond in the last couple months. So if any of you have meshes or point clouds that you want to compress, check it out. If you have issues, make comments, because we've added probably 60 new features based on just requests in the last couple months. So I'd love to hear some more feedback. So that's kind of it. We have time for questions. Maybe I'm not sure what the time is, but if there are questions, I'm here. Yeah? Is there a microphone or anything?
I tried Arno. You talked about Ambisonic on 16 channel, but as of today, Omnitone just gets like first order Ambisonic. So could you tell us a bit more about next iterations of Omnitone and where it's going to get to those 16 channels?
Sure. So for folks that aren't familiar, Omnitone is an open source JavaScript HRTF binaural rendering tool that's also from Google. And the question is, today it supports higher order ambisonics in there. I don't have a time when, but it should be soon.
Excellent talk. Thank you for this. I've got a question regarding Draco. So you talked about compression. Are you also thinking about streaming? So how will you stream the data? Will you use WebRTC, other streaming protocols?
We haven't really considered the protocols so much. We've been more just packing it as small as possible and then expecting, say, the viewer side to load the binary or load the package. We're working with groups like Kronos and GLTF, which is a 3D transmission format, to include Draco as a compression format for that data. There's some open discussion right now on their project online that you can read up on and see our spec on what we want to do with that.
Okay, thank you.
Cool. Bet one more maybe, and then
sure.
then people have to mob you afterwards. Your pick.
He's had a question for a while.
So I just wonder about apps and/or software programs to generate the point clouds. Mm-hmm. Are there any, like, not to give commercial ads, I mean, even better, open source, if there's anything?
I don't have any offhand. All the tools that we've been working with are just internal. Not so much proprietary, but more just internal use, just because there's not a whole lot of stuff out there.
Okay, cool, thanks.
Well, yeah, thank you, Jamieson. Fascinating stuff. Yeah, great talk. Cheers.